Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
Planetoid.
I love that word.
Hello and welcome to Diffusion. Sit back and relax while we uncover weird and wonderful science deep inside your brain. I'm Ian Woolf. On this edition, Dr. Daniel Mansfield talks about strange geometry in Antiquity.
Numbers were used to count, but soon they were also being used as abstract symbols for states of being. Values were given to mass, speed, inertia, and the forces of gravity. Man was learning to numerically relate and to predict. But the magnitude of the calculations necessary made many such theories impractical.
Strange geometries. Exact sciences in Antiquity. Mathematics has been touted as the universal language. But Dr. Daniel Mansfield has found that your culture affects what kind of geometry you develop. Dr. Daniel Mansfield is a lecturer in mathematics at the University of New South Wales, who's been looking into how the culture of the ancient Babylonians led to a completely different geometry. The system we're taught in school is base 10 numbers, and our geometry is based on ancient Greek astronomy. The Babylonians used base 60 numbers, and as a result their calculations of land use were easier than ours. I spoke with Daniel by Zoom and began by asking him how long ago did the Babylonians live in ancient Mesopotamia?
That's about 4,000 years ago.
4,000 years ago. So that's well before Pythagoras and the sort of geometry we learn at school.
Oh yes, absolutely. So the pyramids, for comparison, are a sprightly 1,000 years old by this stage. It's pretty old.
And the Babylonians didn't use geometry the same way. They have a very different culture to the Greek and Roman one that we've inherited. So they think differently, they thought differently rather.
Absolutely. So there's no such thing as a theorem back then. There's no axioms. Mathematics is very different. If you like, in the Greek tradition of mathematics, you've got these little bits right down the bottom that are called fundamental truths or axioms in mathematics. And based on these small axioms, you might recall things like Euclid's axioms, for example. You build up the whole system based on these fundamental truths. In Babylon, there's no such thing as those fundamental truths. You have stuff that you know, and from it you derive other stuff. None of it is deemed to be fundamental. It's just things you know to be true, and you can work with them to deduce other things.
And our system of geometry, what was its original inspiration? They had a practical application in Greek ancient times for what we use.
So a lot of the Greek geometry is based on looking at the stars. People want to know the motion of the planets, what's going on with the sun and the moon, and computing eclipses. They're very interested in this. And our modern approach to geometry is very much based on, we've inherited that approach. The approach of looking at the world through the perspective of angles. You really want to compute angles because that's what's useful to you when you're looking at the motion of the celestial bodies.
And the Babylonians weren't interested in astronomy in the same way?
Not at this stage. They became interested in astronomy later, but wind it way back to the period I'm looking at. And they're not interested in astronomy in a scientific sense. They're interested in land. So if you like, they're not looking at the sky at all. They're looking at the ground. At about this time, people are starting to realize that land can be owned. And if we're both buying a piece of land, you really want to know where those boundaries are. So the science of surveying becomes very precise around this time to avoid disputes between neighbors, basically. And I think we can all understand that. Very human, a human need to have good boundaries which make good neighbors.
Yes, and it's so long ago. So how do you find out what mathematics they were using and what for?
Let's compare this with ancient Egypt. In ancient Egypt, you have things written on papyrus, which is not easily preserved. So it's very rare to get a piece of papyrus that we can read because it deteriorates over time. The Babylonians didn't write on a medium like papyrus. They wrote on clay. And clay documents get buried in the desert and survive almost entirely intact. And so when archaeologists go to these ancient cities, they dig up hundreds of thousands of clay documents. And the clay documents then go to private collections, libraries, museums around the world. So there's hundreds of thousands of these things lying around the globe. Most of them are receipts. So-and-so bought 12 oxen for this much silver, and they're very, very uninteresting. Others are literary works, poetry, letters. The ones I'm particularly interested in are the surveying texts that have been written by a surveyor marking out the boundaries between land. There's not that many of them around. I think, say, from this particular period, there's about 20.
When did we in the modern world learn to read the clay tablets so we understood what they said?
Relatively recently, say about the last 100 years, people have learned really the grammar and have an understanding of what's written on these things. The Chicago Assyrian Dictionary, I think, took decades to write. It's very comprehensive, but it's really just this huge effort of scholars, many scholars over many decades to figure this out. Fortunately, the language has a lot in common with other languages from the area, like Hebrew, other Arabic languages. So it's not like we're starting from scratch, but there's certainly been a lot of effort in understanding what the words mean.
And they used a different number system to us. They didn't count in base 10.
No, they didn't count in base 10 at all. But that's just the tip of the iceberg. So let's start by thinking about time. So we still use base 60 time. 60 seconds makes a minute, 60 minutes makes an hour. So we still, if you like, we still use their number system even today, 4,000 years later. What's different about their number system? Well, there's two things really. The first one is they don't believe in a decimal point or a base 60 point or any kind of point. To them, there's no radix point. It's technically called a radix point. They don't believe in that. So 1 to them could mean 1 hour, 1 minute, 1 second. It's all written the same way. It's all just 1. This makes the operation of division and multiplication very easy. You never have to worry about where that decimal point went. If you want to halve something, it's just, you want to halve an hour, it's just 30. And you want to halve a second, well, it's the same operation. It's still 30 of whatever the next unit might be called.
So there's lots of fractions in a 60.
Okay, so 60 is a wonderful number to use as a base, precisely as you say, because there's lots of fractions. You want 1/5. Well, that's just 12. You want 1/6. That's just 10 in their system. Remember, they don't have a decimal point. So we might say 1/5. If we believed in decimal points, we'd say 1/5 is 0.12 in base 60. So yeah. They don't say 0 and they don't say point. They just say 12. So it makes some things very easy, like division. Division by 5 is now easy. It's the same as 12. It's just multiply by 12. They don't believe in things like a seventh because 7 doesn't divide 60. So that's not a thing to them. Sorry, you can't have 1/7. And if the text says you are supposed to divide by 1/7, they'll just say, no, 7 does not divide. We're not going there. They might make some kind of approximation to it, but they prefer these exact fractions, ones that can be expressed precisely in base 60.
And does your recent work go back to any particular tablets that have been found recently?
Yes. So my recent work goes back to a tablet in the Istanbul Archaeological Museum. So it's a surveying document that was found in Separ, what was once called Separ. And it's a very lovely survey of a relatively small piece of land. It's quite marshy, and the surveyor's done a really precise job about marking out where the marsh is and where the boundary between the land that's been purchased is and the original land. So someone's got a large piece of land, they sell off a slice of it, and the surveyor says, here's the boundary between the new land and here's where the marsh finishes. and so now owns a threshing field and a tower. Kind of boring administrative stuff like that. Unless you're looking for practical applications of geometry, in which case the precision of this document really shines out at you. I've seen a lot of very old documents and new ones, and they usually go like this. They usually go, some surveyor comes along, approximately measures the land, doesn't really care how precise things are because it's just an approximation anyway. Maybe they've been called out to measure, to approximate the size of the harvest. So things like precise boundaries, no, don't care about that. I'm only here to measure a harvest. Even using precise units, I'm not going to bother with that. That's approximately 7. You know what? I'm going to call it 8 because 8's nicer to work with. So precision's not important. And then you get this one. And the person's measured it so precisely. So very precisely. And that's the first thing that stands out. The second thing is the right angles on this document. So the Babylonians don't believe in angles, but they love perpendicularity. And somehow this person's really managed to nail down the perpendicular lines. Again, when you've got old documents, they just have a best guess at it. They're like, oh yeah, I think that's perpendicular, and I'm only here to approximately measure the size of the harvest, so close enough is good enough. And then this guy comes along and his rectangles are so precise. Now, normally you need very, very precise equipment to make perpendicular line. In modern surveying, you'd have your theodolite and you've had lasers and cool equipment like that to make an accurate perpendicular line. They don't have any of that stuff. So the question I wanted to know was how they could make the lines so correct. How could they make these right angles so right? And that's where the geometry comes into it. So can I tell you a story that happened to me before we get back onto that? So that's Absolutely. The question. Here's a little story. So working on my family farm, I'm a teenager and I'm the second son. So I always get the awful jobs. My older brother gets the cool jobs. He drives the tractor. He uses the heavy machinery. I get the awful jobs that don't use any cool stuff. And one day he says, okay, Daniel, go build this fence. Build it perpendicular to the existing fence. It's got to be 100 meters long. Make it happen. Here's your barbed wire. Here's your pliers. Off you go. And so I start building this fence. And then I get a little bit along and I think to myself, hang on, this is not quite perpendicular. I'm going to have to start again. So I pull it all out and I start making it again. And then I start doubting myself again. And I was like, oh no, this isn't quite correct either. And I'm on my third try when my brother comes along and he says, Daniel, where's my fence? You've been here for ages. And I tell him, I can't quite get the perpendicular angle correct. All I've got is barbed wire and some primitive tools. How do you expect me to make a perpendicular fence? And he says, step aside. And he gets the measuring tape and he measures 4 along the original fence. So 4 meters, say, 3 meters in the direction approximately we want to go, and then 5 meters between those two endpoints, making what's called a 3-4-5 right triangle. Of course, 3 squared plus 4 squared is 5 squared. So mathematically, this is perfect right triangle. And I'm gobsmacked because I'm supposed to be the mathematically inclined one. And I've just wasted, all these hours pulling down and remaking a fence. And he just turns up and shows me how it's done. So coming back now to Babylon, how did they make the right angles so precise? So on this plan in Istanbul, I was hoping to find something like the 3-4-5 right triangle, or maybe appearing as a rectangle. Instead, I find 3 of these Pythagorean triples, but they're different. There's the 5-12-13 and the 8-15-17 Pythagorean triples. So not the ones I was expecting, but these other ones. And I'm thinking, why these ones? Why would you use these? Here I am thinking, best case scenario, I find 3-4-5. No, and instead I find these kind of more exotic ones. So why would you have those? The plan, unfortunately, doesn't say why you'd have those, but there's a good reason why you would want to, a mathematical reason. And that's because the sides are factors of 60. 3, 4, 5 is fantastic because 3, 4, and 5 are all divisors of 60. So that would be great if you can use that. But for some reason, maybe they're choosing them for what, I don't know how they're choosing them. But if you can't use 3, 4, 5, your next best guess is to use something that's still got factors of 60. So 5, 12, 13 is great. So it's a great second guess because 5 is good. That's a factor of 60. 12 is a factor of 60. 13 is not, but you've still got 2 out of 3. So 5, 12, 13 is still a pretty good, useful triangle to you because it works nicely in your number system. Similarly with 8, 15, 17, you can still work with that. 8 can be made to work with 60 because it's just 2 and 2 and 2. 15's fine. 17, not so good, but hey, at least you got 2 out of 3. So these are the useful ones to them. These rectangles that have some sides which are factors of 60. And the reason for that is because you can take these sides and numerically you can work with them. You can take the number 15 to them and you can stretch it out to any amount. First you divide by 15, which is, for them is just multiplication by 4, and then you stretch it out to however what long you've got. You can do that with 12 as well. You can't do it with 13. 13 for them, like 7, wouldn't divide. So they just go 13. Now, give up. That's not going to work for me. There's no such thing for them as 1/13. That's not a number. But 1/12, no troubles. That's just 5.
You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Did they have drawings or how did
Absolutely.
this information
So they've
come?
got these tablets, these are surveying tablets. They usually start off with something rather bland, like here is a field, it's this big, and then follows a drawing of the field with all the rectangles sketched out on it and the right triangles sketched out on it, and the lengths of the various sides. So it's quite lovely because you can see in this case, all the Pythagorean triples just sitting there on the map because they've been placed in there on the boundaries to produce those right angles.
So they're able to be very exact without having any sort of computation or other clever ways to do calculations because their number system works well with the geometry.
So they've chosen specific objects, geometric objects that work well in their number system. So it's not an accident. They've deliberately sought out that 5, 12, 13 right triangle because it works in their number system. In our modern mathematics, we tend to work the other way. We say, this is the object we want, and we'll bash the numbers into place to make it happen. So you get things like the square root of 2, which doesn't really fit within a decimal system. You have to approximate it. Instead, they would say, well, I'm going to work with something that fits in my system because computation is hard. I don't have a pocket calculator that can just approximate the square root of 2 for me. So instead, I'll use something that's easy to work with, such as the 3, 4, 5 right triangle.
So the shapes they built were all based on what was easiest to calculate in their number system.
Absolutely. And that's a tradition that goes way back. So if you have a large field and you need to calculate its area, instead of calculating the lengths exactly, they'll just round it to the nearest convenient number. So if you've got something like, as I said before, if you've got a length that's 7, they don't like working with 7. They'll just approximate that to 8 because that's nicer. So you see this real preference for easy numbers to work with. And as society gets more complex and as surveying becomes more precise, they've still got that emphasis on shapes that are easy to work with, numerically easy to work with. They want it to be precise, but they still want that, but they also want it to be manageable in their computational system.
So the applications were mainly to working out areas of land for buying and selling and for building things?
We don't know about building things. The only documents we have so far are about measuring land. Now, that's pretty much all I expect to see. I think that was it. And that's because if you look at the educational texts, the practical applications of geometry are always phrased in terms of land. So you have these very contrived examples of, divide land between 7 brothers, or divide land between 2 brothers, approximate the area of this land. It's like a school textbook that has a whole chapter on land measurement and how to survey land. And that's the end of geometry for them. There's no how to build something going straight up. I think that's probably more like if it goes straight up and doesn't fall over, it's fine. They didn't get that scientific. Good, not falling over is good enough.
And so, is there ways in which this geometry is different to ours? Is it mainly just that it's more precise?
The main way that it's different to ours is through the number system. So geometry and algebra, if you like, go hand in hand. And so if you change your algebra and your numbers, then you get a different kind of geometry. So objects that exist in our system, like say half a square which has diagonal root 2, so half square with sides 1 and 1 has diagonal root 2, don't exist in the same way in their system. They don't have the privilege of saying something is the square root of 2. They might approximate that, and sometimes they've got very, very good approximations to that. But it's never an object in their system, and they don't really want to work with it if they can avoid it. It's more of a kind of theoretical interest to them. Other ways in which their system is different is they don't believe in zero. Zero is not a number to them. And they don't believe in factors in the same way that we believe in factors. So they don't believe in multiples in the same way. And that's kind of interesting because a lot of modern cryptography and so on is built on the idea that you can't factorize a number easily. So how about I pitch it to you this way? They don't believe in factors in the same way we do. So the other thing that's different for them in their arithmetic is the way they think about multiples. So in modern mathematics, you have this idea of multiples, and the basic idea is that it's difficult to find when something is a multiple of a number and when it's not. And a lot of modern cryptography is based on this computational difficulty. They have a very restricted view of what is considered a multiple and what is not. And basically what they'll do is they'll look at the final 2 digits of a number, and they'll use that to decide whether or not a multiple exists. Kind of like in decimal, how you can look at a number that ends in 5 and you'll say, that's going to be a multiple of 5. Or you look at a number that ends in 2, 4, 6, or 8, and you'll say, great, that's going to be an even number. That means it's divisible by 2 or is a multiple of 2. They do the same thing, but they do it with all the factors of 60. And all the factors of 60 squared as well. They'll look at the final 2 digits of a number and they'll say, 1845, that's clearly a multiple of some huge number. And that's how they determine when things are multiples and when things are not. So for them, factorization is easy because they only consider factors that are easy. Again, they're operating in this restricted computational world where it's really, relatively to us, quite difficult to make computations. And so they only choose to make computations that are feasible for them. They're not going to consider multiples of 7 and divisibility by 7. That doesn't work in their system. But numbers like 4, 3, and 2 really work very nicely in their system. And so they will consider multiples of those. And anything that's hard, they'll just say, no, we're not going there. And it's really surprising how much they're able to do with that restricted view of the world. They're able to make these enormous calculations because the computations are relatively easy for them. They're able to make just mathematically perfect perpendicular lines in surveying. Again, because they're choosing the geometric objects that are easy for them to work with. They're
choosing to use the objects that fit, that are easy to work with, rather than forcing what they want into the calculations.
Exactly. And that's the approach we normally take with modern geometry. We say, we want a rectangle that looks with these dimensions. One side of length 1, another side of length 2. Well, guess what? That messes up your diagonal severely because you can't really work with the square root of 1 squared plus 2 squared, which is 5. That's very difficult to work with. And so we, in our modern mathematics, we just say, it's the square root of 5. Whatever that might be, go ask your calculator. They don't have that calculator. They can't just appeal to the magic box that tells them approximately what it is. So they shy away from those kinds of things and prefer instead to use the things that fit.
That was part 1 of my conversation with Dr. Daniel Mansfield from the University of New South Wales about the very different geometrical system the Babylonians developed from their base 60 counting system. Listen next week for part 2. And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker, or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions, and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. The news music was Rhinos Theme by Kevin MacLeod of Incompetech.com. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including Radio Blue Mountains 89.1 FM in New South Wales, 8CCC in Alice Springs and Tennant Creek, 2 MVR in Nambucca Valley, 3 MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, and 2XXFM in Canberra. Diffusion is narrowcast on Indigo FM 88 in northeast Victoria. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, then you can explore more than 1,000 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Make a donation through paypal.me/Ian Woolf, or join my patrons at patreon.com/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits: photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.